Have you ever noticed this? Water vanishes from streets, from clothes, from a glass sitting perfectly still, and yet none of it ever boils. So where does it go? Does water quietly boil at room temperature, or is something far stranger happening? By the end of this video, this will never feel mysterious again. You'll understand exactly how water can disappear without ever boiling. But first, we need to challenge what temperature really means. We're taught that water boils at 212 degrees Fahrenheit. Below that, it should stay liquid. And yet, it doesn't. So the explanation can't exist at the human scale. We need to zoom in. Way in. What looks calm to us is chaos at the molecular level. Inside that glass, water molecules are in constant motion, colliding, bouncing, changing direction billions of times per second. They never stop, not even for an instant. And here's the key idea. Temperature does not describe how fast one molecule moves. It describes the average. Some molecules move slowly, some move faster, and a tiny fraction move far faster than you'd expect. These extreme molecules are statistical outliers, rare, but powerful, because speed is energy. The faster a molecule moves, the more kinetic energy it carries, and kinetic energy is what allows matter to break free from bonds. So if some molecules already carry enough energy, why doesn't all the water disappear? What stops them isn't temperature, it's the liquid itself. Inside the water, every molecule is pulled in all directions by its neighbors. These attractions constantly drag molecules back in. So even a fast one usually fails to escape. Not because it lacks energy, but because it's surrounded. But the surface changes everything. At the surface, there are no molecules above, nothing pulling downward from the top, only from the sides and from below. For the first time, escape becomes possible. Not likely, just possible. In a moment, this will also explain why wind makes clothes dry faster. But first, let's slow things down and watch one single molecule escape. When a fast enough molecule reaches the surface with sufficient energy, it escapes the liquid. It becomes vapor. This is evaporation, no boiling required. But escaping isn't free. To leave the liquid, a molecule must break the attractions holding it inside. That requires energy. This energy is called latent heat of vaporization, and it never comes from nowhere. It comes from the surroundings, the air, the ground, sunlight, and even the water itself. Because the fastest molecules escape first, the liquid left behind loses energy. Its average molecular speed drops, which means its temperature drops. This is evaporative cooling. Boiling is different. At the boiling point, molecules throughout the liquid gain enough energy to escape all at once. Evaporation only needs a few, at the surface. Now we can answer this. Why does wind speed things up? Because wind removes vapor molecules from the surface, making room for more to leave. You've seen evaporation your entire life. You just never saw the invisible part. Water doesn't need to boil to escape. It only needs a few fast molecules at the surface.